Welcome to this explainer. Today, we're unpacking the totally fascinating engineering behind these silent guardians that keep our modern power grids alive. You know, whenever you're driving down the highway or just walking through your neighborhood, you see those massive metal towers and thick cables carrying electricity. But we rarely stop to think about the unsung heroes sitting right between the wires and the steel, the line insulators. Honestly, without these brilliant pieces of engineering, our entire modern electrical infrastructure would literally just melt down. So let's dive right in with a super fundamental question. How exactly do we safely move hundreds of thousands of volts of power through the sky without causing, catastrophic short circuits? Electricity, by its very nature, is always looking for the absolute easiest, fastest path straight to the ground. And those giant steel towers holding up the power lines, well, they're perfectly conductive paths right into the earth. If a live wire touches that metal tower, all that energy instantly escapes. Boom, massive failure. So how do we hold these highly charged wires up with steel without actually letting the electricity touch the steel? To figure this out, we're going to follow a clear roadmap today. First, the function of line insulators. Second, their engineering design. Third, insulator manufacturing materials. Fourth, flashover and pollution effects. And finally, insulator maintenance and protection. All right, starting off with Section 1, the function of line insulators. Let's see how this all builds, starting with the immense physical and electrical pressures these devices have to handle. They actually serve a really vital dual purpose. On one hand, they have to provide absolute electrical insulation, basically preventing any current from leaking out of the conductors and into the metal towers, even when dealing with massive operating voltages or sudden electrical spikes. But on the other hand, they are doing some serious heavy physical lifting. I mean, they have to securely anchor incredibly heavy metal conductors to the towers. They're surviving thousands of pounds of tension, the raw weight of the cables, not to mention the punishing forces of wind, rain, and outdoor pollution. Really, they are the ultimate multitaskers of the grid. And you can see how this works because the grid scales directly with power, right? And so does its defense. Take a relatively lower high-voltage line at 69 kilovolts. That might only need a string of 4 to 6 insulator discs. But as the power scales up, the defense has to step up too. To stop a massive 765 kilovolt surge, engineers have to chain together up to 35 individual insulator discs. That dramatically increases the size, the weight, and obviously the cost of the entire tower structure, all just to accommodate these massive safety chains. Moving on to Section 2, the engineering design of insulators. Now that we've got a handle on the sheer brute force they deal with, let's look at the specific physical architecture engineers use to actually build them. Out in the field, you're typically going to see two main structural forms. First, there's the highly modular cap and pin design. Think of this as a stackable system, where each disc has a metal cap on top and a pin on the bottom. They link together, forming a flexible string. The beauty of this design is that if just one disc gets damaged, you swap it out. You don't have to throw away the whole string. Then there's the long rod type. This is a solid one-piece cylinder of insulation, and it's often used in substations where you really need a rigid, immovable structure. Now, here is where it gets really fascinating, the unique shape of the insulator itself. If you've ever glanced up at a power pole, you've probably noticed they look like little stacks of upside-down umbrellas, or bells. Engineers actually call them petticoats. Now, you might be thinking, oh, that's just to shed rain. And yeah, while that definitely helps, the real reason is purely electrical. That familiar umbrella shape is deliberately contoured to match the invisible equipotential lines of the electrical field. By shaping the physical material to parallel these unseen lines of force, engineers dramatically reduce the stress on the insulator and stop current from leaking across the surface. It's literally shaping matter to match invisible energy. How cool is that? Which brings us to Section 3, insulator manufacturing materials. So what do we actually build these specific shapes out of to guarantee they survive decades out in the elements? Well, we've got a classic materials showdown here. For a very long time, porcelain was the absolute king of the grid. When it's highly pure and homogeneous, meaning no internal air bubbles, porcelain brings incredible compressive strength. Plus, it has amazing electrical resistance, capable of blocking 60 kilovolts per centimeter of material. But it has a serious rival, glass. Glass is totally transparent, which means inspectors can literally just look right through it to check for internal defects. It also has less thermal expansion, so baking in the hot sun all day won't cause it to expand and crack as easily as porcelain might. And, as a bonus, it's generally cheaper to manufacture. But the real kicker here, the crucial point, is that glass actually has a hidden superpower when it fails. If a porcelain insulator takes a hit or gets overstressed, it might form this tiny, almost invisible microcrack that slowly degrades the system until it fails catastrophically. But glass? Glass completely shatters upon severe impact. Now, rather than a bug, this is a brilliant design feature. It means maintenance crews driving by or flying over in a helicopter can instantly spot a missing disc from the ground. They can find and fix failures rapidly, way before the whole grid goes down. We aren't just relying on old-school ceramics and glass anymore, though. Today, engineers also use modern rubber and polymer alternatives. Built from reinforced plastics and silicone rubber, these composite insulators are a fraction of the weight of their glass and porcelain cousins. But their true magic lies in their surface chemistry. They have this amazing, innate ability to make water bead up into separate little droplets. This stops moisture from spreading out into a continuous, unbroken sheet of water. And that is absolutely critical because a continuous sheet of dirty water is the perfect bridge for electricity to escape. Let's look deeper at that in Section 4, flashover and pollution effects. Because nature definitely doesn't make things easy, bringing us to a really dramatic man versus nature conflict on the grid. Actually, the greatest threat an insulator faces usually isn't from the high-voltage wire inside, it's from the world outside. When industrial dust, exhaust fumes, agricultural chemicals, or even sea salt drift through the air, they stick to the surface of the insulator. When you mix that dry pollution with just a little bit of moisture, think morning fog or a light drizzle, it creates a highly conductive muddy soup. And this triggers a highly dangerous event called a flashover. A flashover is essentially a massive electrical short circuit where the current completely bypasses the insulator by ripping right across its polluted outer skin, jumping straight to the metal tower and instantly knocking your power offline. And, pollution isn't the only villain here. These insulators have to constantly absorb immense overvoltage shocks. Imagine a power line suddenly taking a direct hit from a lightning strike. The insulator has to absorb that millions of volts spike without shattering. But overvoltages don't just come from the sky. They can be generated internally by the grid itself. Sudden switching operations, like a massive circuit breaker opening or closing, can send a tidal wave of excess voltage down the line. Plus, phenomena like ferroresonance or the Ferranti effect on very long transmission lines can cause voltage to surge dramatically. The insulator just has to hold the line against all of these sudden electrical earthquakes. To stop these electrical jumps, especially over polluted surfaces, engineers meticulously calculate two different measurements. First is the clearance distance. That's simply the shortest, direct straight line through the air between the highly charged wire and the grounded metal tower. But the real defense is the creepage distance. This is the total surface path the current must literally crawl or creep over to cause a short. Because electricity will follow a wet, dirty surface much easier than it will jump through dry air, engineers design those umbrella-like shapes to make the creepage distance incredibly long. They force the electricity to take a tortuous, winding path over ridges and under eaves, ensuring the physical surface path is much, much longer than that direct path through the air. All of this leads us to Section 5, insulator maintenance and protection. Let's see how grid operators actively fight back against these relentless natural forces. Because as you can imagine, you can't just install these things and forget about them. To combat all this buildup, we go to some pretty extreme lengths. I'm talking about deploying helicopters to pressure wash insulators dangling hundreds of feet in the air. But here's the absolute kicker. They do this while the line is entirely live. They don't shut your power off. How is that even possible? Well, they use highly purified, completely distilled water. Pure water actually doesn't conduct electricity well at all. It's the minerals and impurities in everyday water that carry the charge. By blasting the insulators with pure, non-conductive water, they can scrub off the pollution, the salt, and the grime without electrocuting the helicopter or interrupting the city's power supply. It's wild. Or take the sheer ingenuity shown on the Greek island of Crete. Being an island, their power grid is constantly battered by fierce ocean winds carrying highly conductive sea salt. It was causing constant flashovers and required non-stop cleaning. So, to combat this aggressive sea salt pollution, engineers started coating the insulators in a specialized, highly water-repellent wax. This wax forces any salty moisture to bead up into isolated droplets rather than forming that dangerous, continuous conductive sheet we talked about earlier. This simple chemical intervention broke the electrical path on a molecular level, drastically reducing outages and saving massive amounts of money on constant washing. So the next time you flip a switch, give a little thought to those stacked discs hanging quietly in the sky. They balance raw physical strength with invisible electrical barriers. battling lightning, pollution, and quite literally the sheer weight of the world. But as our global power demands soar to historic highs, and our climate throws harsher, more unpredictable elements at these silent guardians, what invisible engineering marvels will we have to invent next to keep the lights on? It's a challenge that will absolutely define the future of global energy. Thanks for joining me on this explainer, and keep looking up.